Hey everyone, and welcome to this explainer. Today, we're diving into something that's going to completely transform how you look at software delivery. We're pulling some absolutely critical insights straight from Chapter 18, Observability for CI/CD Pipelines. Now, think about it. We spend so much time and money observing our code once it's actually running in production, right? But what about the massive, complex machinery that actually gets it there? Today, we're taking those exact same rigorous principles of modern observability and applying them directly to our CI/CD pipelines. And let me tell you, this is a total game changer. If you've ever felt that excruciating pain of a sluggish deployment or just wasted your entire afternoon fighting a broken build, well, get ready because we're about to fundamentally flip the way you think about shipping code.
Okay, let's dive into this because we've all been there, haven't we? You write your feature, you push your code, and then you just sit there. You're staring at a spinning icon, blindly waiting for a build to finish, just crossing your fingers that a test doesn't flake out for like the third time today. Honestly, it kind of feels like you're manually driving the Mars rover, dealing with this agonizing minutes-long delay between sending a command and actually seeing what happened. So the question we really need to ask is, why do we put up with this? Why on earth do we treat our delivery pipelines like these opaque, unmanageable black boxes when at the exact same time we're demanding total transparency and sub-millisecond telemetry from the apps they're deploying?
But hey, before we get too deep into the weeds here, let's just quickly establish our baseline definitions, just so we're all speaking the same language. When we say continuous integration, or CI, we're specifically talking about that automated process of taking your source code and its dependencies and turning it into a compiled build artifact. And then continuous deployment, or CD, is taking that newly minted artifact and safely rolling it out to production. Together, they are literally the heartbeat of modern engineering. They're what closes that critical feedback loop between you writing logic and actually seeing it run in the wild.
All right, here is our roadmap for today's explainer. First up, we'll tackle the opaque box problem. Then, we'll look at getting the best ROI in observability. Third, mapping the CI/CD ontology. Fourth, setting metrics and SLOs. And finally, we'll wrap it up with a real-world case study from Honeycomb.
Let's jump right into Section 1, the opaque box problem. When your CI/CD setup acts like an opaque ox, you are basically flying blind. As a developer relying on that platform, you never really know why a build suddenly takes twice as long, or what actually caused an end-to-end test to flake. You don't even know where to start fixing it. And don't even get me started on why the pipeline infrastructure bill is so astronomically high at the end of the month. There's a huge financial and cognitive cost here. It's so frustrating to have that huge delay between writing code and knowing if it actually works. You end up context switching and boom, your focus is just gone. And if the pipeline eventually goes green, we just shrug and assume it's fine. But the reality is, we have absolutely zero visibility into its actual health or how close it is to completely falling over. Moving right along to Section 2, Best ROI in Observability. I want you to really let this paradigm shift sink in. Quote, CI/CD pipelines are, at their core, production systems for developer feedback. That is huge. Think about it. Developer time is incredibly expensive, right? We literally cannot afford to waste those valuable cognitive cycles waiting on unpredictable systems. The faster, the more deterministic you make your builds, the faster your team can push changes, get real user feedback, and actually establish a reliable rhythm. So when you optimize the pipeline, you're not just saving a few compute credits, you are essentially multiplying the effectiveness of every single engineer in your org. The old way of doing things? It treats CI/CD as a total afterthought. It's viewed as this necessary evil, a chore, or just some black box owned by a distant release team. But the new way, the path forward, demands that we treat our pipelines with the exact same rigorous, measurable production standards that we use for our customer-facing apps. We're talking about establishing service-level agreements, maintaining active on-call rotations for pipeline health, and using actual telemetry to debug failures. Platform engineering teams can just exponentially magnify their impact by eliminating these specific delivery bottlenecks. Honestly, it's arguably the single highest return on investment an engineering team can make.
All right, Section 3, Mapping the CI/CD Ontology.
Now, what's really interesting about this slide is how we actually fix this. To turn that frustrating opaque box into a transparent glass box, we need a shared ontology. We have to map our CI/CD concepts directly over to the concepts of distributed tracing. Now, you might be wondering, why tracing? Why not just use our normal logs? Well, traditional logging just spits out disconnected, sequential text entries. It tells you that something happened, sure, but it really struggles to show causal relationships or things running concurrently.
Distributed tracing, though, it gives you exact causality, duration, and hierarchy. So if a build takes 20 minutes, tracing will explicitly show you, hey, this database container took 15 of those minutes just to spin up while your integration test sat there waiting. That level of visibility is exactly what lets engineers stop guessing and actually start knowing.
So here is how the translation actually works. It's like a giant puzzle coming together. Think of a full CI/CD workflow. That's the entire sequence triggered when you push code. We map that to a single distributed trace. The root of that trace is your total pipeline duration. Now, inside that workflow, you have a job, like running a linter or compiling a binary. That maps perfectly to a set of spans underneath the root trace. And finally, an individual step inside that job, say running a specific shell script, becomes a single span within its parent job. By mapping things out this way, we don't have to go invent some entirely new dashboarding system. We can just use the incredibly powerful observability tools we already have to analyze our builds the exact same way we analyze web requests.
This brings us to Section 4, Setting Metrics and SLOs. Okay, so how do we start getting this actionable data? It's a simple 3-step progression. Step 1, just start exporting the start and end times of your individual jobs, plus whether they passed or failed. Easy enough. Step 2, though, is absolutely crucial. You have to attach the repository and branch context to that data. Why? Because you desperately need to know if these tests are running on the main branch or just a pull request. Think about it. A flaky test on a PR slows down one person, but a flaky test that merges into main, that brings the entire team's delivery to a screeching halt. Then, step 3 is taking all this beautifully structured data, defining implicit service-level indicators, and setting actual service-level objectives to hold the team accountable for build reliability.
To do this right, there are 4 essential SLIs you've got to track. First, typical success rates. Second, overall latency. And by that, I mean the actual end-to-end time a developer is sitting there waiting. Third, flake percentages. You can easily measure this by tracking jobs that fail, but then miraculously succeed on an immediate retry without any code changes. And fourth, infrastructure resource usage. Now, gathering this data is a total game changer because it completely kills what I like to call team folklore. You know team folklore? It's when developers say stuff and stand up like, oh, the integration suite just kind of feels slow on Tuesdays. That stuff destroys morale. With these SLIs, you replace those fuzzy feelings with hard telemetry, proving exactly where the friction is so you can go fix it.
And this brilliantly illustrates our next big leap. We have to stop looking at jobs in isolation. Developers don't wait for one single step. They wait for the whole validation sequence. In modern pipelines, these sequences form a directed acyclic graph, or a DAG. That's just a fancy term for a network of tasks where execution flows in one direction. Like, task B can't start until task A finishes. By visualizing this entire graph as one distributed trace, you can find the critical path. That's the absolute longest sequence of dependent tasks that dictates your total build time. This is literally the most important thing. If you spend 2 weeks optimizing a 10-minute job, but it's not on the critical path, you've saved your developers exactly 0 minutes. Tracing shows you that critical path instantly. Also, getting rid of test flakes and making things predictable, it's not just about keeping your developers from pulling their hair out. It's a massive factor in your infrastructure economics. CPU power is expensive. When your tests are robust to timing variance, meaning they don't just randomly fail because the CPU got a little throttled, it enables much higher infrastructure packing ratios. That basically means you can squeeze a lot more concurrent jobs onto a single compute instance. If your tests are flaky, you're forced to run them in total isolation, wasting tons of idle CPU just to prevent weird failures. Make them predictable, and you can run way more work on fewer CPUs without paying the annoying penalty of retrying flakes. It saves a fortune.
Finally, let's look at Section 5, the honeycomb case study.
I want you to remember this one fundamental truth. Undeployed code is perishable. Just let that sink in for a second. When a build system is painfully slow or just totally unreliable, pull requests sit there, and they age like milk. An aging branch is a huge liability. If it falls out of sync with main, you get horrific merge conflicts. Developers lose all their context, and you waste so much effort just trying to keep the code relevant. The longer it sits undeployed, the higher the chance it's going to break the whole system when it finally does go live.
The engineering team over at Honeycomb recognized this reality head-on. A CI/CD build system is a mission-critical, complex system. It is literally just as vital as your production database. Think about it. If your build system goes down, deployment stop. Full stop. You can't ship new features, and way more terrifyingly, you can't ship emergency bug fixes. You are completely paralyzed. Realizing this meant they had to stop treating their pipeline like a second-class citizen.
They actively applied observability-driven optimization to it, treating build outages with the exact same severity as production outages, and it kept their developers secure, happy, and shipping fast.
Let's move to and see how this builds out in the real world. Honeycomb achieved this transparency without inventing some crazy proprietary format. They just used the OpenTelemetry Standard, or OTel. They hooked up their GitHub Actions environment directly with OTel collector receivers. So instead of relying on clunky webhooks or trying to scrape text logs, the runner environment itself creates rich, structured spans for every single job and step. Those collectors then securely route the telemetry right to standard OTLP destinations. It's such a brilliant, elegant way of using modern observability pipelines to treat build data with the same respect as high-value production data. It gives you total visibility into the execution graph.
So, I'll leave you with this. If your build system goes down today, or if it's just agonizingly, painfully slow, how long will your code perish? Really give that some thought. Treating your pipeline like an opaque box is a luxury that no modern engineering team can afford anymore. But by mapping out that tracing ontology, tracking your core SLIs to kill off that team folklore, and visualizing the critical path of your build graph, you can absolutely shatter that black box and turn it into glass. And when you do, you are going to massively accelerate your team's ability to ship software safely and confidently. Thanks so much for joining me on this explainer, and I really hope you're ready to bring some total transparency to your own delivery pipelines. Catch you next time.